The storms we chase are leading us, and love is all we'll ever trust. Yeah, no, I don't wanna waste what's left. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go. Finding life along the way, melodies we haven't played. No, I don't want no rest. Echoing around these walls, fighting to create a song. I don't wanna miss a beat. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go. And we'll grow in number, fueled by them to see the horizon, turn us to thousands. And we'll grow in number, fueled by them to see the horizon, turn us to thousands. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go.
Buenas, buenas. Acá andamos otra vez. Bueno, vamos a estar viendo The ODIN Project nuevamente. En este caso vamos a estar viendo un poquito sobre ciencia de la computación, creo que es. Toque esto. Por acá y ahí estamos. Bueno, vamos a ver. Okay. Claro, por eso algunas personas que antes de hacer ODIN hacen el curso de Computer Science de Harvard, creo que es el CS50, para tener unas buenas bases sobre eso. Pero bueno, llegado el caso, veremos. Overview of topics. Un algoritmo y que es un pseudocódigo. Y nos da para ver un video. Ok, o sea, voy a parar la música para poder ver eso. Vamos a ver introducción a los algoritmos por David Maran. Es una charla TED. Ok. Vamos a agrandarlo. Creo que lo tengo por acá. Esto no. Estoy buscando el audio del escritorio. Esto no. Audio de escritorio. Bueno, ¿dónde está la fuente del audio? Esto no. Bueno, vamos a agregarlo. Em, Estoy buscando a ver por qué no tengo. Acá no. Ah, ok, está como.
What's an algorithm? In computer science, an algorithm is a set of instructions for solving some problem, step by step. Typically, algorithms are executed by computers, but we humans have algorithms as well. For instance, how would you go about counting the number of people in a room? Well, if you're like me, you'd probably point at each person, one at a time, and count up from 0. 1, 2, 3, 4, and so forth. Well, that's an algorithm. In fact, let's try to express it a bit more formally in pseudocode, English-like syntax that resembles a programming language. Let n equal 0. For each person in room, set n equal to n plus 1. How to interpret this pseudocode? Well, line 1 declares, so to speak, a variable called n and initializes its value to 0. This just means that at the beginning of our algorithm, the thing with which we're counting has a value of 0. After all, before we start counting, we haven't counted anything yet. Calling this variable n is just a convention. I could have called it most anything. Now, line 2 demarks the start of a loop, a sequence of steps that will repeat some number of times. So in our example, the step we're taking is counting people in the room. Beneath line 2 is line 3, which describes exactly how we'll go about counting. The indentation implies that it's line 3 that will repeat. So what the pseudocode is saying is that after starting at 0, for each person in the room, we'll increase n by 1.
Ok, espérame un chiquitín. No tengo el... A ver si está... Spanish. Ok, eso para acá.
Now, is this algorithm correct? Well, let's bang on it a bit. Does it work if there are 2 people in the room? Let's see. In line 1, we initialize n to 0. For each of these 2 people, we then increment n by 1. So on the first trip through the loop, we update n from 0 to 1. On the second trip through that same loop, we update n from 1 to 2. And so, by this algorithm's end, n is 2, which indeed matches the number of people in the room. So far, so good. How about a corner case, though? Suppose that there are 0 people in the room, besides me, who's doing the counting. In line 1, we again initialize n to 0. This time, though, line 3 doesn't execute at all, since there isn't a person in the room, and so n remains 0, which indeed matches the number of people in the room. Pretty simple, right? But counting people one at a time is pretty inefficient too, no? Surely we can do better. Why not count 2 people at a time? Instead of counting 1, 2, 3, 4, 5, 6, 7, 8, and so forth, why not count 2, 4, 6, 8, and so on? It even sounds faster, and it surely is. Let's express this optimization in pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. Pretty simple change, right? Rather than count people one at a time, we instead count them 2 at a time. This algorithm's just twice as fast as the last. But is it correct? Let's see. Does it work if there are 2 people in the room? In line 1, we initialize n to 0. For that one pair of people, we then increment n by 2. And so by this algorithm's end, n is 2, which indeed matches the number of people in the room. Suppose next that there are 0 people in the room. In line 1, we initialize n to 0. As before, line 3 doesn't execute at all, since there aren't any pairs of people in the room. And so n remains 0, which indeed matches the number of people in the room. But what if there are 3 people in the room? How does this algorithm fare? Let's see. In line 1, we initialize n to 0. For a pair of those people, we then increment n by 2, but then what? There isn't another full pair of people in the room, so line 2 no longer applies. And so by this algorithm's end, n is still 2, which isn't correct. Indeed, this algorithm's said to be buggy because it has a mistake. Let's redress with some new pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. If one person remains unpaired, set n equal to n plus 1. To solve this particular problem, we've introduced in line 4 a condition, otherwise known as a branch, that only executes if there's one person we could not pair with another. And so now, whether there's 1 or 3 or any odd number of people in the room, this algorithm will now count them. Can we do even better? Well, we could count in 3s or 4s or even 5s and 10s, but beyond that it's going to get a little bit difficult to point. At the end of the day, whether executed by computers or humans, algorithms are just a set of instructions with which to solve problems. These were just 3. What problem would you solve with an algorithm?
Interesante. A ver, watch. ¿Qué es un algoritmo? YouTube for more structured look at solving problem. Ok. Vamos a ver eso. Segundo. Vamos a ver los títulos. Ok. Para acá.
What is an algorithm? Algorithms are one of the most basic building blocks of computer software. every piece of software you interact with, from your...
Ok, aguanta un poquito. Vamos a poner English, Spanish. Spanish, Spanish, Spanish. Spanish. Ok, vamos para atrás.
What is an algorithm? Algorithms are one of the most basic building blocks of computer software. Every piece of software you interact with, from your smartphone to your web browser to your coffee maker, uses an algorithm somewhere. So what is an algorithm? An algorithm is a set of step-by-step instructions that is used to do something. With a definition that broad, it's not surprising that they are in everything. It might surprise you that you yourself probably use algorithms in your day-to-day life, even if you don't call it that. If you sort your laundry before washing, first let me say good for you. Second, you probably do it following an algorithm. Take a piece of clothing. If it's white, put it in the left pile. If it's colored, put it in the right pile. Repeat until you're done. That's an algorithm. The power of algorithms comes from the fact that computers can follow these steps quickly and very precisely. For example, how do you look up a name in the phone book? If you're like me, you plop the book open somewhere. If you've gone too far, open a spot closer to the front. Otherwise, move toward the back. When I feel like I'm close, I start going page by page, looking at the first or last name to know if I've gone too far. Computers can do better. A phone book is essentially just a sorted list of names. If you have 1,000 pages in the phone book, you can use an algorithm called binary search to require at most 10 page turns. It works like this. Say that you're looking for Jill Jackson. Start in the middle at page 500. The first name on this page is McDonald, so we've gone too far. We know the M in McDonald has to be after the J in Jackson, so the right page is before page 500. Divide the pages in two again and turn to page 250. This time the first name on the page is Flores. Now we've gone too far to the front. There are 250 pages left, so we divide by 2 and turn to page 375. We repeat this process until we find Jill Jackson, which will be at most 10 turns. This might be difficult for you or me, doing math on the fly and turning directly to the right page, but a computer has no problems with this. And an algorithm like this is efficient in terms of the computer's processor, meaning it scales amazingly well. This process takes 10 steps in a 1,000-page phone book. If we switch to a phone book with 100 million pages, it would still only take 27 steps. Algorithms can also do more complicated things. PageRank, the algorithm underlying Google search results, is one example. There are lots of pages on the internet that talk about cheese. If you search for the word cheese, which results would you expect to get and how would they be ordered? A naive approach might be to rank most highly the page with the most occurrences of the word cheese. Unfortunately, that breaks down pretty quickly when you think about a very long page with just the word cheese repeated over and over. While it might have the most occurrences of the word cheese, it probably isn't the page you want. So how does Google do it? In the early days, at least, they used an algorithm called PageRank. They start the algorithm by crawling every page on the internet and keeping track of what other websites link back to that page. The logic goes that an important page will have many more links pointing at it from other pages than an unimportant page will. Each link is also scored, with links from other important pages being worth more than lesser links. The logic behind that decision is that if your page is linked to by whitehouse.gov, Wikipedia, and the New York Times, those three should be worth more than links from your 10 best friends websites. At the beginning of the algorithm, each page is given a starting value of 0.25. As new pages and links are explored, the score for each page is updated. A link to a page confers that page's own value divided by the number of links on the page. In other words, if a page has a value of 0.25 and only has one link, that link will add 0.25 to the page it links to. If it has 5 links, each of those links is worth 0.05, 1/5 of the original value. After crawling the entire web, each page ends up with a score ranking its importance. When you search for a phrase, you are given a set of results based on the content of each page, does it match your query, as well as the page's importance, does Google give it a high PageRank value. Google's system has evolved and become more sophisticated, but PageRank remains a defining algorithm of the web. Algorithms underlie all the code running everyday things like the internet to the most sophisticated machine learning projects in the world. Underneath the covers, they are really just following a set of instructions, an algorithm.
Ok. Algoritmos. Bueno, vamos a poner esto por acá. Y vamos a poner esto. Subir un chiquitín más por acá. Vamos a read this core question about dice leer esta pregunta en Quora sobre la importancia de los algoritmos en el desarrollo web para obtener contexto por qué estamos viendo esto. Ok, vamos a leer. Ok, estamos. Vamos a aumentarlo. No. The significance of algorithm in English with application are nothing but crap. Those with apps that contain some serious data processing are flawed by design and should be free of any other processing. This operation basics fitness purposes. I propose that Mary should need to know a specific algorithm for image processing, audio processing, HTTP, to get a web development job. And during the web development, it can be however useful to become familiar with the computational complexity theory to avoid design performance inefficient classes or methods. Performance optimization. Fire. Bueno, está hablando sobre los algoritmos y cómo optimizar una aplicación web. Claro, cuando tienen mucha demanda en una web. Power access to resources such as TV, reduction web service costs, cable search, getting rid of long queries that slow down projects. Claro, no es que vamos a inventar algoritmos super nuevos, sino que vamos a estar usando algoritmos que ya existen o herramientas para ayudar a la eficiencia de nuestra página. Claro, we use framework 6 for process. Those companies invade the Claro, no es que vamos a reinventar la rueda, sino tenemos que usar las herramientas que ya existen y que fueron creadas para solucionar eso, ¿no? Such as Ruby, puede ser. Software engineer, that's computer science. They invented their own wheel because it is the only thing computer science people learn while they were in school. Don't do that. Don't do it. Hands off from companies require reinventing algorithms or processing large amounts of data in web apps. If some web applications are expert system for some apps, etc., they may require algorithms from some expert domain. However, I disagree with data processing done in web apps and suggest we should use highly optimized solutions for that, such as Adobe, etc. And include it doesn't matter how many million people use your web app. There is load balancing and multiple nodes running your app in a cluster, each server getting only some number of people depending on the server utilization. So we are down to create web apps, load balancing, separate big data processing, and there are also special tools for real-time big data processing such as Storm and others. Companies have no excuse for demanding knowledge of actual development for web development jobs. Está bien. There is no difference in DB select in a big web app, not a small web app. Okay. No hay diferencia en la selección de una base de datos de una aplicación grande o una aplicación web chica. There is only fitness and purpose. Sometimes SQL is fit, other times no SQL is fit. That is an engineering task to evaluate, justify, choose the right tool for the job. But no knowledge of algorithm or science is needed. In fact, all these computer science people who claim they are engineers and who never study engineering are commenting here rubbish about how algorithms are important for high traffic webs, when in fact there is no any high traffic open source portal or website to contain any CS computer science algorithm. See Liferay or hybrids, for example. The computer science people are being anonymously wrong. Large-scale web apps require knowledge of software engineering, no computer science. you don't need an algorithm left, right, or habits. There are typical huge experience portals in high traffic scenarios such as banks, insurance companies. They have load balancers, no computer science people invading a room like crazy. Computer science people you're assigned even suggesting that websites are optimized at the primitive level of algorithms. Bien, tiene sentido lo que dice. Vamos a estar usando herramientas básicamente, frameworks o cosas así. Muy interesante. ¿Qué es el pseudocódigo? Vamos a ver esto. Ok. Vamos a parar la música. Toque. Vamos a subir acá. Vamos para acá y vamos a replay.
So this is a quick tutorial making sure that you understand exactly what pseudocode is. I've had 2 questions in this via email, and I want to make sure that before going on to the other tutorials or working with the other exercises, everyone understands what pseudocode is. Pseudocode is just an English-like way to state an algorithm. It's like communicating with somebody regarding the instructions which will solve a problem. I have 2 problems here written on the screen that I'll go through, make sure you understand the problem, and then I'll write the simple pseudocode for it. It's important to know pseudocode is not syntax, although as you get more and more experience as a programmer, your syntax or your syntactic tokens will kind of creep their way into your pseudocode, but just because that's kind of the way you're thinking. So write a pseudocode. See that I have a typo there. Write a pseudocode solution for taking in 2 integer values, and your solution should output the sum and the product of those numbers. If I'm to write pseudocode for that, I just give myself a little bit of room here. I know that I would first need to prompt the user for number 1. And once I do that, I have to make sure that I save whatever they entered into a variable. And in my pseudocode, I like to go ahead and reference the variable names. Then I know I need to next prompt the user
El segundo número.
for number 2 or second number.
Guardar la variable.
And now I need to make sure I save that input to num2.
Okay.
And then I just have to compute the sum and the product of those numbers and then output the information. So
una variable para almacenar la suma.
I should have a line that says sum equals num1 plus num2. And then I should have another line that says
El producto.
product equals num1 times num2. And then last but not least, I simply need to output the sum and the product. I can say output sum, or I can say print sum, print product. So you see, even though it's kind of difficult to communicate while I'm typing this stuff out, it is very important that you understand that pseudocode is just a way of talking through your algorithm. Now, is this the exact and only way that this particular problem could be solved? No, there's several different algorithms you could have come up for this problem. But each of those different algorithms would have their own little pseudocode, just an English-like way to solve the problem.
Estamos aprendiendo a programar.
So, let's go through this next one, and then I believe you should have pseudocode down pat. If not, contact me again. Write a pseudocode solution which will take in an integer value and determine whether that value is odd or even. So we have to come, even though we're so intelligent, we can look at a number now and determine if it's odd or even. Since we're writing an algorithm or instructions for the computer to do it for us, of course we have to get down at the lowest level and find instructions for each action. So the first thing we need to do is acquire the number. Prompt the user for the value. Why don't we say for the number, save input to num, and then we're going to check to see if num mod 2 is equal to
0.
1.
Ah, ok.
If it is, print the number is odd. Put quotes around that so you know it's going to standard output. And then we just say if it is not, print the number is even. So there's simple pseudocode solution for this problem. You're just taking the number in from the user. You're calculating to see if whatever that number, mod 2, is equal to 1. And if it...
Bien, estaba sobre un pseudocódigo se usa mucho para aprender al principio. Muy interesante. Vamos a ver qué es lo otro. Métodos recursivos. A ver que si tengo un assignment acá. Ok. Tengo video, lectura. Ok. Métodos recursivos. Okay. Recursion is the idea that a function is called itself. O sea, la recursividad es la idea de que una función se llama a sí misma. Pretty simple, right? It's used to check the big program and start breaking it down into smaller pieces. Divide and conquer and continue to feed the solution back into the original function until some sort of answer is achieved and the whole chain wins. In computer science, divide and conquer is an important algorithm design paradigm based on multi-branch recursion. A divide and conquer algorithm works by recursively breaking down problem into or more subproblems at the same override type until this becomes simple enough to solve directly. The solution to the subproblems are then combined to give a solution to original. Claro, lo que dice es que un problema lo tenemos que dividir en pequeñas partes y a medida que vamos resolviendo cada una de esas partes pequeñas vamos a resolver todo el problema general. También hay una forma correcta e incorrecta de usar la recursividad. The fact is, any problem you can solve recursively, you can also solve using the iteration that you know. Por ejemplo, los ciclos for, while, for each. If you find yourself saying, why I don't use just a while loop here, then you probably should have. You won't often end up using a recursive solution to a problem but you should get a feel for when it might be a good idea. Some problems also break down into far too many pieces and totally overwhelm your computer's memory. There is a balance. In this brief lesson, you will get the chance to learn more about when and how to use recursion, and then in the next project you will get the chance to apply some of that, since it probably won't really stick until you have a chance to try it. Overview. This section contains an overview of topics that you will learn in this lesson. Why recursion is a useful technology for solving problems. What are the limitations of using recursive solutions? What type of problem are more suited for simple loops than recursion? What is meant by recursive depth? What is Stack Overflow, the concept of the website? What is the relevance of recursive problem? Ok, vamos a poner un poquito de música. Tengo bastante para hablar sobre recursividad. A ver. Ok. O sea, cuando una función se llama a sí misma, es recursividad. Dos formas de pensar. Esta es la potencia. Ok, acá hemos visto la potencia manualmente, paso el número y el índice. Dice hay dos modos de implementar esto. Uno es usando el loop, por ejemplo. Tengo la función. El resultado va a ser ok, y menor que n, por ejemplo que n es 3, va a ser x por x n cantidad de veces. Bien. pensamiento recursivo simplifica la tarea y se llama a sí mismo. Por ejemplo, si n es igual a 0, a 1, entonces regresa a ese. Si no, hace x por hace x por pues, a ver, acá entiendo que llama a la función. Dice, por favor, cuando la función es llamada, dice la ejecución se divide en dos ramas. Si n es igual a 0, es x. Bien, pero si es distinto, llamo a la función. Si n es igual a 1, entonces este es tribal. Es llamada recursión base porque inmediatamente produce el resultado obvio. De otra manera, podemos representar función potencia como x por en matemáticas x a la n es igual a x por esto es un we transform text into simple action duplication and simple code of the same task. Next step, simplify the for. So we can also say how you count yourself. Por ejemplo, para calcular la potencia de 2 a la cuarta, la variante recursiva hace esto así. ¿Por qué lo hace al revés? Por ejemplo, para calcular la potencia de los cuatro de la recursión grande C. Será 3 a la 2. Si la recursión usualmente es más corta. necesita X tanto. Mm, 8. N-1. Si yo pongo a ver, voy a abrirme algo. Parece bien. Mm, 8. Y si le pongo 2, 4. Porque hace 2. Em, 2. Ok. Si le tiro un 4 va a ser 2 al cubo. 2 por 2, 4, 2 por 2, 4, 2 por 4, 8, 16. Si hago 4, 16, 32. Ah, ok, entendí. Execution context. Ok, ahí. Bueno, nada. Voy a dejar por acá y a la tarde continúo con esto. Saludos.